Okay, welcome back everyone. Sorry this one's a little late. I had some technology issues while doing my first recording of this. Apparently my audio didn't record, so I had to basically redoing this again. So hopefully this works out this time, or I'm going to be very unhappy. So continuing on from what we stopped with last time, there was a couple more things on how we can actually form molecules. Both of these are not very likely, but just in the interest of completeness, we're going to mention them. So we do have the possibility of collisional association. Essentially, this is when you have A and B and they collide with some inert intermediate, which is able to take away that excess energy, and then we form our compound AB, and then that inert intermediate basically just goes off. So this is really going to be very, very unlikely because this is going to be a three-body collision. And three-body collisions, as you can imagine, are going to be extremely rare in an area where two-body collisions are rare in the first place. So three-body collisions are going to be extremely rare. Rates for this are on the order of 10 to the minus 32, which if you look back is much, much lower than any other rates that we were dealing with. Although the units on this are centimeters to the sixth per second. The reason this is centimeters to the sixth rather than just cubic centimeters is because we are dealing with three bodies over here. So basically we have that extra cubic centimeter come in, which is why this is centimeter to the sixth. But in either case, these rates are ridiculously low. So don't expect them to occur very, very likely. The final one here is associative detachments. Again, this one is also not very likely. So we have here a neutral colliding with an anion, and then they make your molecule AB and eject the electron. Now, the reason this is not very popular is that anions are not very abundant in space. As you can imagine, if I have an anion, very easy to get ionized by some photon and then just become the neutral. So you're not going to have very many anions actually around in space. And later on, when we start looking at all the different molecules that have actually been seen, anions there have actually been a couple of instances where they've seen them, but the vast majority are actually going to be cations, actually in outer space there. But yeah, you're not going to see anions very, very frequently. As you can imagine, the ionization energy of any anion is going to be much, much lower than that of the neutral because it's just easier to remove that extra electron. Now, the one where you do have the associative attachment, the only one that would be particularly relevant, you have a hydrogen atom with a hydride anion to make H2 an electron. This one has a decent rate, 1.3 times 10 to the minus 9 cubic centimeters per second. And this is probably how hydrogen was made before there were dust grains. We talked about this a couple of weeks ago. How hydrogen, H2 molecules are actually formed by two hydrogen atoms colliding with a dust grain and then bouncing around until they eventually find themselves and form a H2 molecule. And that's actually going to be much faster than this rate. But in the early universe, before dust grains were around, this was probably the predominant way that hydrogen molecules were actually formed. So what we're going to talk about the rest of the day today is talking about the trihydrogen cation, or H3+. When I was actually looking for some graphics for this, just through the Google image search, came up with this lovely little picture here. This was actually from the Chemical Engineering News over there where they actually talked a little bit about it. But yeah, that's it's a very unexpected thing. Here is essentially we have our two hydrogen atoms, and then we have another hydrogen on top of there. From your Gen Chem experience, this would seem to be very, very wrong, but it is actually a thing. And you have to realize, of course, we have here 3 protons and 2 electrons. This makes it actually the simplest polyatomic molecule around. All right, and for that reason, it's actually very important computationally speaking, and also from astrochemistry perspective is also extremely important. Now, how do you actually draw the Lewis structure of this? Essentially, every time you see it, it's just 3 hydrogens arranged in a nice little equilateral triangle, because you have to realize the Lewis structure, every bond, of course, represents a pair of electrons, but there's only 2 electrons in this entire thing. So it's not like a nice little resonance structure. Lewis structures really don't work very well in trying to draw this, at least from a Gen Chem perspective. Essentially, what we have here is the electrons are essentially just being shared between all the 3 of these protons as they're going around, just trying to keep everything together. So here's a brief little history of H3+. So it was actually found much earlier than you were probably suspecting. It was initially detected back in 1911 with J.J. Thomson. So he was working on cathode ray tubes, and he found something that had about 3 times the mass of the hydrogen ion, and he correctly identified it as an H3+. Now this is the picture from his paper. Now unfortunately it's not a great image. I think it's just because when they were scanning these things in, they were just scanning in black and white, and if you're dealing with shades of gray on these things, it just didn't pick up very well. But fortunately, right next to it over here, he had his little key to represent what all the little splotches on his photographic plate actually represented. So down here was 16. That was probably just some oxygen contamination which was in the system. Over here would be like the proton, and then we'd have essentially the 2, which would be like an H2 plus, and then this streak, which is very, very difficult to see over here. That's probably the H3 plus. So if you're looking, what is the earliest image of H3 plus? It's over here. And so essentially this was just an early version of mass spectroscopy that he was actually working on and identifying the different ions that were actually in the system there. So as I said, it is the simplest polyatomic ion that there is. And at the time, there was actually some belief that there was also a neutral H3 molecule. And there was actually a lot of searches for this through the 1920s. They tried to figure out how this would fit in computationally with the quantum mechanics and the quantum chemistry that was coming out at the time. But eventually they kind of realized it's probably not going to be a molecule, and if it is, it's not going to be very, very stable. So they really kind of fell out of favor, and they really weren't looking for it. However, they did find spectroscopic evidence, actually, of the neutral H3 molecule in the 1970s. So this was late 1970s by Hertzberg. And this, again, is not going to be stable in a ground state. These were all Rydberg transitions. So for a Rydberg transition, this is essentially we have a very highly charged ionic core, and then we have an electron which is way over here on the outside. So you basically, here's your little neutral atom, and then out on the outside here, there's going to be your electron, basically just barely keeping the thing together. So really, you could think about it like an H3 plus molecule with a little Pluto electron kind of going around on the outside. That's basically just making the thing neutral. But there is no stable ground state for the H3 molecule. It's totally repulsive. So that's why H3 molecules in the ground state, you just don't see those. All right, here's a little bit better image of H3 plus. Again, this was kind of just using an earlier version of mass spec, so they were just kind of doing ion counting in this case here. And now initially when Thomson was doing it, they did not know about deuterium. So a relevant question you may have is, well, wait a minute. Well, if I have this H3 splotch over here, how do I know that it's not H3 plus and it's not instead HD plus, which would also have a mass of 3 times that of the hydrogen or the proton? Well, as you know, deuterium is about 10 to the minus 4 times as abundant as the proton. So even if there was a little bit of HD plus, and I'm sure there probably was a little bit of HD plus, it would be way, way, way below this value over here, because here you can see here's my proton, here's my H3 plus. It's way, way bigger, and if it was HD plus, it wouldn't make sense that it would be actually this big. Especially if you just compare this to like the H2 plus, well, you would expect an HD plus and an H2 plus to have similar intensities, but since this is so much bigger, it actually points to the fact that a lot of H3 plus was actually being formed in their system, and there really wasn't quite as much free protons around, and there also weren't that many H2 plus molecules around, because again they would react with a lot of neutral hydrogen atom or hydrogen molecules that were in the system. And this is just a consequence of the system that he was using. Basically these little peaks over here, as they were going through the mass spec, some of the H2 plus or some of the H3 plus, they might have been in vibrationally excited states, and they broke up during transits, and because of that you basically get these little mini peaks off to the side. So that's what these are representing over here. Right. So yeah, like I said, H3 plus, much greater abundance than your HD plus. Now, this again, this was from 1925, that experiment. In the 1930s, there was some quantum chemistry being done by Coulson and independently Hirschfelder, and they determined that the ground state is an equilateral triangle, and there are no excited electronic states, and all the vibrations were in the infrared region. So this is why we're not going to talk about any electronic spectroscopy of H3 plus, because it doesn't have any bound electronic states. There's just repulsive states. There's a possibility of a weakly bound triplet state, in which case both electrons are have the same spin, but there has been no experimental observation of that as far as I know. So it's such a high energy level that it's not really known if that's actually going to be stable. It's like I said, it's barely bound if it does exist, so it could just be a little bit on the other side and then be completely repulsive. So for all intents and purposes, there are no excited electronic states for this. But also very usefully for us, these vibrations are all in the infrared region. Okay, so there was a lot of work being done computationally. They're using this to test their early theories of computational chemistry, but there really wasn't anything to compare to through the 1970s, because all they had was the observation of this in the mass spec, but until you actually have a way of probing the energy levels via spectroscopy, you don't really know how good your calculations actually are. And also there were some hints that this was going to be important for interstellar chemistry, based upon some of this computational work, but again, there was no spectroscopic identification. And then in the late 1970s, Oka started doing the search for H3 plus in the lab. And next week we'll probably be talking about all the experimental things behind this. And he didn't succeed until 1980. Was when he had the first spectroscopic identification. And by the way, Oka turned out to be my graduate advisor when I was in grad school, so that's why I happen to have some familiarity with a lot of the materials that we're going to be talking about here today. And by the way, even though he didn't prefer being called Dr. Oka, he just told everyone, even his undergrad students, just call him Oka. So everyone always just called him Oka for that. Anyway. As for the H3+, here is the first line that was actually seen. Now, you'll notice this has kind of like an unusual line shape, and again, we'll talk more about this when we do the experimental part about this. But normally you would expect a line to kind of increase like a nice little Gaussian line shape, but what this is actually a first derivative Gaussian line shape. And the reason for that is for the experiment, he was doing velocity modulation. So you have an ion, and then you have an alternating voltage, which is basically Doppler shifting the ion into and out of resonance with the beam that's coming there. And because of that, you wind up getting this first derivative of a Gaussian line shape for that. So that's how you can actually observe this. And nicely, when you went and velocity modulated the ions, neutrals obviously don't velocity modulate because they're not going to be affected by an electric field that's going back and forth. So this way, the ions, which are going to be in much lower abundance than the neutrals, are able to be detected because they're going to give this nice little line shape, which you can lock into with phase-sensitive detectors and basically couple the signal for those out. But you can ignore any absorptions from neutral molecules, which are probably going to swamp the entire system. So that's why it has this kind of unusual line shape. But again, we'll talk more about that. So I'm going to get to the experimental stuff. Okay, so here are the first lines that were actually observed, and these were again compared to the calculations that were actually done. And there's 15 lines that were actually observed here. So those were the first 15 lines that were measured. And from that point, I believe there's been like over 1,000 lines that have actually been measured. So over here, basically the two strongest transitions, these are the ones that are going to be most important from an astrochemistry perspective because they are the most intense, and therefore they're going to be the easiest to actually detect. And right here, this nu2, this is the vibrational transition. So this right here is your ground state, and then this is going up to the first vibrational state for that. So once he had the spectroscopic identification of the line, he went and tried to detect this in interstellar space, because now once you know what you are actually looking for, the properties of that line, the intensities, and that all the computational work was basically verified, you can basically ask for telescope time and look for the absorptions in regions where you think H3+ might be found. Now remember, he first found it in 1980. So essentially he was searching for another 15 years until 1996 when there was the first successful detection at UCIRT. And this stands for the United Kingdom Infrared Telescope, and it's on Mauna Kea, which of course is in Hawaii on the Big Island. So here, these are the two stars that they're basically looking at, and you can see that these absorptions here are just barely above the noise floor. If you were just taking a regular spectrum and you had no idea what you were actually looking for, you would probably just skip right over these. But fortunately, since they knew it should be in this region, and once correcting for the Doppler effect from the Earth's motion around the sun, and also the motion of the cloud and everything, they were able to successfully identify that these two little blips right here are actually due to the H3+. And over time, again, you have to remember, this is 1996, so we're talking over 20 years. The spectrometers and everything at the telescopes have gotten much, much better. So these little blips here and the signal-to-noise ratio have all improved over time for those. As for these little blips, we're able to figure out that they corresponded to a column density of around, I think this one was about 4, this one's around 6, times 10 to the 14th per square centimeter. So again, it's a pretty standard value for most clouds for these. Now, interestingly enough, while they were searching for the H3+ in interstellar clouds, there was actually the first non-terrestrial detection in 1987, which happened on Jupiter, and they also later found these things on Uranus and Saturn. And what happened there, and we'll look at some pretty pictures here in a minute, they actually didn't find the lines that they were looking for. They actually found completely new transitions. So here's some of the transitions, and just for reference over here, remember this was basically around 3 microns, or about 3.6 microns or so, and that's basically around 2,000 some wave numbers. This over here is actually at 4,000 wave numbers. So these are not the same transitions that they were seeing in the lab. In fact, up to that point, no one actually had thought to search out that far for H3 plus transitions because they were mainly interested in astronomically relevant sources. And it's usually cold in space, so therefore you wouldn't expect to see a very large population of these. But of course, in the upper atmosphere of Jupiter, there's a lot of energy being pumped in from the magnetic fields and everything. So you have enough energy to actually excite these H3 plus molecules quite a bit, and they basically compared this with some laboratory some laboratory searches as well, and they nicely agreed. So it's fairly confident that these observations over here match up. And I think actually after they detected it on Jupiter first, and then once they did that, they went back to the lab. And since they knew what they were looking for, they went and compared and actually did see that. And again, they also compared very nicely to the ab initio calculations, usually within a wave number or so. Over here, this is the assignments for basically the rotational quantum numbers. We'll talk a little bit about these later on. But for the interstellar observations, these are all going to be like low quantum states. Basically your J is like 0 or 1. But as you can see, these are very, very hot. We have very highly excited states here, some up to 10. In some cases, so we do have very excited states actually being seen for these transitions over here. And this was actually, so obviously here's your little data table. There's actually, keeps going on, but I didn't include the whole thing for space. And then over here, depending on how well this actually shows up, we have essentially this is the observation for A here. This is a, the A is down here actually. Yeah, the A, which is for the non-auroras over here. And basically, I mean, there's like this little one over here, but a lot of these other lines really aren't seen very well. On the other hand, for the B, this is for the auroral parts, and you can see that in the auroras, this is where a lot of the H3 plus are actually being observed. So the auroras, of course, that's when the solar wind collides with the upper atmosphere and excites, in Earth's case, nitrogen and oxygen to emit light. Well, in Jupiter's case, since it's mostly hydrogen and helium, can basically ionize some of the hydrogen, make H3 plus, and you get very hot H3 plus molecules up there. And this is a good way that you can actually probe some of the dynamics of the aurora. You can figure out stuff about the temperature, about your ion density, and a whole bunch of other information from that that you can see. And similar things have occurred on Saturn and Uranus as well. So as you may be aware, around Jupiter right now there is the Juno spacecraft that's observing it. And this is actually some of the data that came out. So here is basically a visual image of the aurora that's coming off of there. And then this is for the northern hemisphere, and then here is a observation for the southern hemisphere. And then over on this side, this is where the spectrometer is basically what it's looking for is the H3 plus. And you can see how well it kind of correlates between what's basically lighting up over here versus what is actually being seen over here for the abundance of the H3 plus, and a similar thing down here. And this was taken with the GIRAM, the Jovian Infrared Auroral Mapper. And interestingly enough, you'll notice that this right here looks fairly circular, but the one in the northern hemisphere is severely distorted. And that's because, as you know, the moons of Jupiter, the one which is closest in, of course, is Io, the volcanic moon that looks like pizza. This one is close enough to Jupiter, and of course, with all the volcanoes, they're emitting a whole bunch of compounds, and then of course those get ionized in the high radiation field. So there's basically a magnetic field connection between the moon and the planets, and that's essentially what's causing this distortion of the auroral region. And as they basically can map this out. As Io goes around it, basically the auroral oval basically follows where Io is actually going from there. Right. And then basically once you go and you start plotting out how much H3 plus is around there and what your temperature is, what you find out is that this is a very thick layer, 500 to 700 kilometers thick. Now, of course, on Jupiter-sized scales, this is not that thick, but still that's quite an abundance of H3 plus, and no surprise we're able to see that at these fairly high densities. It is also fairly hot, as you can see right here. We're basically looking at temperatures around 700 to 900 to 1,000 Kelvin over here. So these are fairly hot over here, and in fact, in the southern region, it's even hotter, probably pushing up above 1,000 Kelvin here. Also, interestingly enough, the temperature, which is over here, and the density, they're like anti-correlated. So if you look over here, here's basically a lot of H3 plus on that side, and not so much H3 plus on this side. And if you look over here, this is where the hot part is, and this is where a little bit of a cooler part is. Similarly for this one, There's a lot of H3 plus over on the top, not so much here on these sides, but look where the hot parts are. They're basically over here and over here. So this is basically saying that there's kind of like an infrared cooling effect from the H3 plus. So it's like able to get rid of some of that excess energy in the form of the H3 plus and actually keep things a little bit cooler from the surrounding area. So H3 plus, at least in the auroral regions of Jupiter, act as a good cooling agent for the system there. Okay, so we talked a little bit about some of the history about H3 plus. Theoretically, H3 plus is actually very important because this is one of the few molecules that you can simulate from first principles. And when I say first principles, I mean you are able basically to start from Schrodinger's equation and using nothing more than your proton mass, your electron mass, Planck's constant, speed of light, electron charge. You're able to calculate out what the properties of this molecule should be. If you're dealing with more complicated molecules, let's say water, there's just way too many electrons to actually keep track of things. Remember, you only got 2 electrons and 3 protons for H3+. If you deal with, let's say, a water molecule, you have 10 electrons. And you still would have 2 protons and an oxygen nucleus there, which wouldn't be too hard, but still, you're dealing with 10 electrons versus 2 electrons. That's going to be much more computationally difficult, and you're going to need to do a lot of simplifications for that. But if you're just dealing with 2 electrons, it's still extremely complicated. It is by no means trivial, but it can be computationally seen, and it is a good way to essentially test how good your theory is versus how good your approximations actually are. Now, obviously, like a water molecule, you could very easily simulate that, even on a fairly cheap laptop today, within a couple of minutes. But those programs are using a basis set of wave functions. They're basically, not starting from first principles. They're saying, here's the standard building blocks, and we're going to, manipulate those building blocks to get a water molecule. So, as a way of analogy, for simulating water, they're essentially giving you the bricks, and you're building the house. When you're dealing with H3 plus from first principles, you're going there and actually mining the clay, turning it into bricks, and then building the house. So you're basically starting at an earlier stage, and you have a much better understanding about what is actually going on. And also, what is possible, since you are dealing with this from first principles, if you start noticing some differences between theory and experiment, that could be the possibility of pointing to some new physics. Now, as far as I know, there's actually not been any discoveries in that regard because there's still some limitations to this. But if anything is discovered that way, that would be, again, a very valuable discovery to do. All right, now obviously there's going to be a lot for astronomy as well. What is very, very nice about H3+, and a little bit of just luck here, the absorption is in the L window. So this right here is the L window. So this is just showing the transmittance. So in other words, like how much light from the sky can make it to the ground as a function of your wavelength. And this again is in microns down here. So there's these little windows where the light can actually make it through. And over here between 3 and 4 microns, where the H3 plus transitions are, there's very little in the way of telluric contamination. So this means that there's not many like water or carbon dioxide absorptions in this region, so you can very easily have your ground-based telescopes do your spectroscopy, and you don't have to rely on a very expensive space-based telescope. So that is very, very valuable for doing the astronomy here, and why it is so useful for astronomy. Also, it is very simple, so it's easy to model the H3 plus with other simple atoms or molecules, versus if you're dealing with more complicated things like, let's say, water, where you would have a whole host of complicated interactions that could go on because your potential energy surface is that much more complicated. But H3 plus, it's since it is so simple, it has very simple and well understood energy levels, and it makes modeling and understanding of these things a lot easier. As we saw before, it is a very good probe of interstellar chemistry. So we saw that a little bit last time in modeling how the other ions and everything are actually formed. As we saw on Jupiter, it's a great way to probe ionospheres of planets. And as we saw, it's a great way to measure interstellar clouds. So this way we can actually figure out how much the cosmic ray ionization rate is, for example. And there's actually some other useful information that comes out of this. First of all, there's the dimensions of clouds. So this is a very easy way to actually measure how thick your cloud actually is. What is the temperature of the clouds? Which, again, since most of these clouds are very, very cold, you need something that has low energy levels, or close, that has the energy levels that are conducive to making these measurements. So H3 plus is very useful in that regard. As we're going to be seeing, it's useful in determining how dense things are, assuming that the thing is warm enough. Okay, how dense things are, assuming stuff is warm enough there. And later on, we'll talk a little bit about deuterium fractionation, and this is actually going to be very important in actually how molecules with a lot of deuterium in there, actually surprisingly large amounts of deuterium in these molecules actually form. Okay, so over here we have a plot of essentially the number density of hydrogen versus the number density of these other species. So as you can see, for hydrogen atoms, hydrogen molecules, these have a nice linear relation. So as you and again remember these are all logarithmic scale, but at least they're linear on the logarithmic scale here. But as you increase the amount of hydrogen, obviously the total amount of hydrogen actually increases over here. Carbon monoxide and the carbon ion over here, they both basically follow between these two things. However, what you'll notice here for the H3+, it's essentially constant, right? And then for dense clouds, it has one constant over here. For diffuse clouds, it has a different constant down there. So what's going on here is we talked about last time how the density of H3+ corresponds to the cosmic ray ionization rate, your electron recombination rate, and then the ratio between hydrogen and electrons. So over here, of course, remember we talked about how the carbon ion correlates very well with the amount of electrons in there. So that's why essentially this right here essentially just corresponds essentially to the concentration of your carbon ions. So as you can see, the ratio between these is essentially constant. So for that reason, the amount of H3+ as a function of your hydrogen density, because it doesn't really depend on here, they just divide out, works out very nicely that we actually wind up getting a nice flat region over here. And then once you get to the dense clouds, it doesn't depend upon the amount of electrons anymore, because in dense clouds there's not that many electrons around. Because remember, the electrons over here occur because radiation is coming in to ionize these carbons and form the carbon ions and the free electrons. When you get to very dense clouds, a lot of that radiation is being shielded, so you don't really have enough high energy radiation to go about and ionizing things. So you have a lot of neutral material around there. So the way that you have your H3+, of course, it goes and is ionized by your cosmic rays, just like before. But for the recombination, essentially what goes on, the H3+ collides with the carbon monoxide to make the protonated carbon monoxide, and then that is essentially the destruction mechanism while you're dealing with dense clouds over here. So, but again, since the carbon monoxide to hydrogen ratio is essentially constant, that means that the H3+ here, as a function of the number density of hydrogen, is essentially going to be a constant as well. All right. Now, if we were to use, let's say, the amount of hydrogen or carbon monoxide or anything else over here, this would have to essentially have a quadratic dependence. So what we're basically saying is here that the intensity is directly proportional to the path length. So in other words, if I'm observing a cloud, and I don't know exactly what the density is over here, because that can vary, from the inside of the cloud, which could be very, very dense, to the outside of the cloud, which would be not so dense. So you'd have to get some very nasty integrals and try to approximate while the density varies as a function of distance, and it's just a plain old mess. But since this is nice and linear, all you have to do is you get a star on one side, and it goes throughout the entire cloud, and then you just measure out how much H3+ was actually in that entire cloud, and that's going to correspond very well to what the length of that cloud actually is. And if you have a diffuse cloud, you'll just basically use this other number here. Again, it's fairly constant as a function of length, and you have a fairly good idea what your abundance of the H3+ is and what your length of your cloud is. Now, eventually, you get so diffuse that you really don't have that much H3+ there, but in that sense, you really don't have a cloud to talk about, so there's really no problem in those cases. All right, so next up we're going to talk a little bit about the rotational levels of H3+. And these are for the ground vibrational state. Okay, so we're not really worrying about any excited states yet, because again, space is cold. So if you have your H3+ molecules, they're generally going to be only in these lowest states, or that's where you're going to be your significant population. And then when you do get your absorption, it's coming from a background star that's basically encountering this H3+ in the ground state and then going up to an excited state. And then those are going to be the absorptions that you actually see there. Now, generally speaking, since like I said, space is cold, only over here, the 1,0 and the 1,1 levels are going to be significantly populated. All these other levels up here are generally going to not be very populated. Now these arrows are essentially showing the allowed transitions between these different states. And as we look over here, for a lot of these excited states over here, the transitions, their lifetimes are fairly short, at least on interstellar timescales. So for this one over here, we have a 3.8 hour lifetime. This one is 7.9 hours to go down there. This is 16 hours. That's 20 days. This is 27 days, and then eventually it makes it down here. So after a month or two, if they're in these excited states, they basically find their way down here. Now, interestingly enough, this one that goes over here to this level, this 3.3 level, this is metastable. And this metastable state, it's because the transitions that are allowed is, as you can see, only ortho-ortho or para-to-para. So that can go to here, but we can't get a para-para transition to actually occur. So, or sorry, a ortho-para transition to actually occur here. So while these can decay all the way down, this one is basically stuck up here as a metastable state. Eventually, it can basically decay down to here, but essentially you would need this 2.0 level for it to go to. But unfortunately, there's not an allowed state over here. This is because of the Pauli exclusion principle, so this state simply just doesn't exist. And because of that, this level is essentially stuck here. Now, this level is 361 Kelvin above the ground state energy. So if you're in a warm environment, this level here can be significantly populated, and then you can actually record transitions from this level. But as for these other levels down here, you might say, well, these would be populated before this one. But these transitions don't exist long enough. So even though you may have enough energy to get them up to this level, they decay fairly fast. So you're not going to have a significant population of H3 plus in these states or above. But because it's metastable, basically it gets pumped up there and sits there. It's kind of like when you're starting a laser. Remember, the whole idea is you have to basically have a population inversion where you form a lot of your ions or your energy states in the upper state here that's basically stuck up there. So you basically pump everything up to a high energy, and then it decays down to a ground state. Now, you can't really make an H3 plus laser from this because there isn't a allowed transition down to here that's even weakly allowed. But that's essentially the same idea, that these are basically being pumped up there, and then you're going to have a large population in these excited states over here. All right, now the 2.2 state is an interesting case. Notice that its lifetime here is around 27 days, and if you go and kind of work out the math on this, that works out to about a collision time between molecules of about 200 per cubic centimeter. So in other words, if you have this density of ions or atoms and ions in your cloud, basically they would be colliding on the order of about once a month. And so that means if you see a significant population over here, that's because these things are basically bumping into each other. They have, first of all, enough energy to excite it to this excited state, and also enough density that this is being pumped up, collisionally speaking, before it has enough time to actually decay down to the ground state. So if you see like a significant population of this and a significant population of this, that's kind of telling you that we have a very warm environment and a fairly dense environment as well. All right. And then again, there's no transition between these two levels because, quantum mechanics reasons. So basically, these are the two levels that we see significantly populated over here. Okay, now as for the H3 plus levels, the 1, 0, and the 1, 1, so those are those two lowest levels that we saw before. They have spin statistical weights of 2L or 2I plus 1. The I here, that's your total nuclear spin. So this is either going to be 1/2 or 3/2. So the way you can imagine this, if I have my protons, either they can be all pointing in the same direction, so 1/2 plus 1/2 plus 1/2, so that would be my 3/2 over here. Or I could have two pointing in the same direction, and then one pointing the opposite direction, so that would be plus a half, minus a half. So I would have a plus 1/2 being my total spin. So it's either going to be one of these two versions over here. And basically your 2I plus 1, that's either going to give you a 4 or a 2 when you plug those numbers in. So that's going to give you a 4:2 intensity ratio from the spin statistics. And then you take your Boltzmann factor, so essentially the temperature and the energy spacing between them, and the line strength, which is just your transition energies based upon your Frank-Condon factors and everything. It works out that the two lines are approximately equal intensity, and that's why if you look back to the lines that we saw earlier, it's basically, it almost looks like a doublet. You have two lines basically about the same intensity between them. We also saw that, so if you look back on the stuff we talked about last week, looking at Zeta Persei and the stuff they did in the cryo-ring experiment, there was a lot of all those transitions were basically the same intensity there. Now, what you can do for using these other levels is essentially look at the population ratio between the 3.3 levels, which is that metastable state, and the 1.1 level, which is our ground state there. And this one would act as a nice thermometer. So you can essentially just look at those and, again, through a little bit of computation, figure out what those values represent. And then you could also look here at the population ratio between your 2-2 state and the 1-1 state, and then that's going to act as like a densitometer. So it's going to tell you exactly how dense your clouds actually are. As we saw earlier, orthoparatransitions by collisions are actually allowed. So from just by emitting radiation, these are not allowed, but collisionally they are actually allowed, because what's happening is we can have some scrambling of protons going on. So here if I have a H2 molecule and it bumps into an H3 plus ion, what's going to happen is you're going to get an intermediate H5 plus excited state here. And after that, it can just go back to an H3 plus and an H2. Now, it might seem like nothing has actually changed hands over here, but in reality what happened was the proton from this one went over to here. So I've had a proton exchange. So that means if this guy here was ortho before, depending upon how my protons were arranged over here, this guy could easily be para, he could easily be ortho. So there's going to be some mixing of states just based upon the collision intensity between these and how often they actually occur for that. So next up, we're going to talk about the central molecular zone. So this is a region about 200 parsecs of the galactic center, and we're talking again about the Milky Way here. It has about 50 million solar masses, and this is mostly as molecular gas. All right. So here we have some observations. So right here, this red line is representing the H3 plus 3-3 transition. And then this blue line represents the H3 plus 1-1 transition. So essentially what we're looking at is these are when we're starting in our lower energy state being the 3-3 and then going to the first vibrational state. And then down here, again, we're starting from the 1-1 lowest vibrational state or zero vibrational state up to the first fundamental transition vibrational state that we're actually seeing. So this is going to be those transitions that we actually see there. And then down here, we're actually looking at the carbon monoxide absorptions in that same area as well. So what you'll notice is basically a lot of these kind of correspond between the carbon monoxide and the H3 plus transitions. Now, there's a lot of useful information here that if you don't know what you're looking for, it just looks like, okay, that's an interesting blob. But first of all, this is a very, very broad transition. So normally if you just see layer transitions, these are going to be fairly narrow, like the carbon monoxide ones down here. But since this is so very broad, that's telling us a lot that, in fact, that there's a lot of very turbulent gas, and it's also very energetic, also because this is dealing with the 3-3 transition, so it also has to be fairly on the warm side as well. So this is telling us a lot of information there. Also, this is telling us, and the temperature of this works out to about 250 Kelvin for that. The density, as we're going to see on the next slide here, is actually going to be probably around 100 per cubic centimeter. You might notice here, we don't have anything with the 2-2 transition, and that's because the 2-2 transitions apparently aren't very well populated, so that means that our density has to be fairly on the low side, less than 200 per cubic centimeter and probably less than about 100 per cubic centimeter or thereabouts. So notice we have, first of all, some very impressive peaks here at 0 and minus 50 kilometers per second. And also the whole reason we have carbon monoxide down here is because we want something to actually compare this to. If we have carbon monoxide and H3 plus in the same gas cloud, we would expect their velocity shifts, their Doppler shifts to be very similar. And that's what we're seeing. The carbon monoxide over here and the H3 plus, as you can see, those look pretty much bang on. You could almost just overlap the two of them there. And then there's also another maybe a little bit of a peak over here around 100 kilometers per second or so for that one. But obviously these are the two ones that kind of stick out here. So what's actually going on here is, as you'll notice, the 1-1 transition, we see these peaks over here, but we're not actually seeing the peaks in the H3 plus. And that's because, if we have my star over here, and we're observing over here, well, all the gas and stuff is around here doing the H3 the 3-3 transition. But then these other little 1-1 transitions, these are intervening cold gas clouds that are in the way. So whenever you're looking at it, remember, you're not just observing one thing, you're observing everything that's in between you and the actual star there. So that's what we're actually seeing here is the H3 plus from the 3-3 and the 1-1 transitions. These are both going to be in the central molecular zone, but then we have additional 1-1 transitions from intervening dense clouds that are just happen to be in the way, and that's why we're seeing these additional peaks. Also, notice that we're not really seeing any carbon monoxide in the same kind of thing that we're seeing for the hot clouds there. So that means that there's not really that much carbon monoxide in this area. So that means that we're not dealing with dense clouds where it's the energetics are low enough that carbon dioxide molecules can actually freely form. So we're not seeing much in the way of carbon dioxide in the central molecular zone over here. Okay, so here's just another picture. This is from, well, I think, yeah, the same one here, just kind of looking at a different plot of this. And as you'll notice, so here we have the 1,1 transition, here's the 3,3 transition, here's the 2,2 transition, and here's the carbon monoxide transition there as well. So if you notice, again, for the 3,3 and the 1,1, these are fairly, have that very deep dip, so that tells us things are very energetic there. Also see a very large dip here in the 1,1. And again, here's these lines which correspond to my carbon monoxide lines, which is from intervening gas clouds that are in the way over here. But notice here at the 2,2 level, basically, there's nothing there. I mean, if you squint, you may be able to convince yourself there's something there, but there's nothing, at least above the signal-to-noise ratio in the ray of the 2,2 level there. So there's not been any observation of this 2,2 level. Now, because, if you remember looking back at what our levels look like, the 3,3, of course, is higher than the 2,2 level. So there's actually a population inversion going on, which corresponds to what we know about it being a metastable state. So in other words, we have a lot of H3 plus in this 2,2 or the 3,3 level up here, but we essentially have nothing in the 2,2 level. So that means it isn't very dense. It isn't being collisionally excited for that. Also notice we have these very negative velocities over here, right? All these velocities are kind of like moving out this way. And this is actually due to what's known as the expanding molecular ring. So it's not just like a nice little ring of gas around the central part of the galaxy there. It's actually moving outwards from the middle, and it's moving again towards us in this regard. Nothing we have to worry about. I mean, it would take many years before it would get to us anyway. It's so diffuse we really wouldn't even notice anyway. But it is basically expanding outwards from there. All right, so here's just to kind of give you a little bit of a schematic, just to kind of understand exactly what we're actually looking at in regards to these things. So first of all, remember there's no way we can actually get a bird's eye view of the galaxy. We'd have to travel for several thousand years at nearly the speed of light to even hope to get high enough up that you would get like a top-down view of the galaxy here. So really all the information that we're getting about how these arms and everything are arranged, we're basically just doing from our little vantage points over here. Now, how you do this is, of course, first of all, you have the parallax, so you can measure your stars, that are basically in this region over here, surrounding the sun. And then what you do is you see those stars, and then let's say you measure a distance over here to this star, that's that way, and then you view it over this region. And then you would say, okay, well, I'm seeing a dust cloud which are moving at this speed, this speed, this speed, and then you use another star which is basically in the same area of the sky but is much closer, and it's like, oh, I'm only observing stuff that's over here, but I'm not actually seeing all this other stuff over there. So from all those like little pieces of information, you can basically piece together how far each one of these like little blobs are away from the sun here, right? And then once you have that, you can measure your velocities, and then you can essentially just start piecing together exactly like how all these little spiral arms of the galaxy actually are put together here. Okay, so right here, this is the expanding molecular ring, and again, it's kind of like we want to view this from the top down, but again, we are basically seeing this side on. And it's really not a ring per se, really, it's a shell of gas that's expanding, but just because if you think about, if you look at like a view of a balloon, obviously if you look through the middle of the balloon, there's not that much material there, but if you look through the edges of the balloon, there's more material, so it's going to appear correspondingly darker. So that's what we're actually seeing is essentially, this is the outside of a shell. So even though we say it's a ring, it appears to us as a ring from our perspective, but in reality, it's an expanding shell of gas over here that's actually occurring. All right, and essentially, these are just some of the different sources that are inside the ring, and basically just kind of like viewing because they give off a lot of radiation, so you can basically just view how far they're actually, or how fast they're actually moving relative to us. And then this is basically just a bunch of other gas regions and other energetic regions in the area. And by the way, SGR, that stands for Sagittarius. So a lot of the, if you look up in the night sky and you know your constellations, the center of the Milky Way corresponds to the constellation Sagittarius. So the black hole in the middle is Sagittarius A star. So it's actually like right around here. There's a very, very energetic region. So all these things are basically right around the central black hole of the galaxy here. All right, and then here's just another view of this. So this is kind of like zoomed in on this region here, and essentially, it's just a total mess. I mean, you have, there's your black hole essentially, and then you just have like these little tendrils of gas that are kind of moving around. SNR, that's a supernova remnant, and then here we have these other, active sources, and and they're basically just categorized by A, B, C, and so on there. So there's a lot of interesting dynamics that are actually going on with all that. And again, a lot of these things are being probed spectroscopically, and a lot of this is being done in the infrared, because if you have a lot of dust out here, visible light is very easily scattered by dust, so you can't really make good observations with that. But infrared, very easy to actually go through a lot of the dust. So the reason we get pretty high resolution photos of these things is because a lot of this stuff is done in the infrared. So here is another view, basically just kind of like using some of the information we're talking about here. So over here, these were some of the stars that were actually used to probe this area over here. And essentially we have these two little graphs, which you can just figure out computationally. So in this case, we're looking here at the density of H2 over here, and this is the temperature. And then these different curves here are plotting out, well, what is the ratio between the 3,3 and the 2,2 line, and also the 3,3 and the 1,1 line over here. So this way you can basically take the ratio between these different lines here and figure out, well, if I have, let's say a temperature of 600 Kelvin and a density of, let's say, 10, it's going to correspond to a 3,3 to 2,2 ratio of about 20, and then here for a 3,3 to 1,1 ratio of about 1. So you kind of have to follow these curves back here. So essentially that's kind of like the region we're looking at. And then this gradient area, that corresponds a lot to where things actually are in the central molecular zone over here. And then once you have this graph like this, you can actually just invert the graph. And instead of plotting temperature and density on your x and y axes, you can instead plot your the ratio between the 3,3 and the 2,2, and then the 3,3 and the 1,1, and then basically plot out what is the temperature and the density on the curves this way. So it's essentially you just take this graph and invert it. So this way we can get like useful information. So in other words, you just go here, measure what the intensity ratio between these lines are, and then you can very easily figure out what temperature and density corresponds to those measurements. And what we can basically see here, and again, these little arrows correspond to these little crosses over on this side. Essentially, if you remember from the slides we're looking at, the 3,3 to 1 red ratio, that's actually fairly easy to measure. So there's not going to be a lot of uncertainty in this region over here. So these, the error in this regard here is fairly small. So that means we can fairly easily say that our temperature is going to correspond to about 250, 300 Kelvin, somewhere in that ballpark. But our density of our hydrogen, they're going to have a lot more uncertainty. That's why the arrows are so long this way. Because again, there's not a lot of, well, basically there's no 2,2 intensity for these things. So essentially you're almost dividing by 0. So what you're basically saying is we're starting off at a certain point saying, well, this is the minimum resolution our spectrometer has, so this would be basically down here. And then you're basically just going up because you don't know exactly what it is. So it could be anywhere from, let's say about 100 down here or below that. That's all you can really say because, the 2,2 level has such a low intensity to it. Okay, so for the H3 plus molecule, there are 3 potential vibrational modes that you can have. First of all, there is the symmetric stretch mode, which is going to be infrared inactive because this essentially is just taking your protons and then they're all stretching equal and opposite on every side here. So again, there's no change in dipole moment for this one, so this is going to be infrared inactive. It's around 3178 wave numbers for this. For the bending mode, those are in fact infrared active because as you can see here, we're going essentially from an equilateral triangle to an isosceles triangle, so you're going to have a change in dipole moment in that case. So these are going to be infrared active. These two are actually degenerate. So a lot of times what's going to happen is you're not going to get either one or the other, but it's going to be some linear combination of these two bending modes. And when that happens, essentially what you get is your molecule is going to be kind of like twisting around here. So basically your protons are going to kind of go like in this area or like this or like this, and they're basically just kind of like spinning around as everything is kind of twisting around there. So it's just a linear combination between these two bending modes. And this is going to correspond to the vibrational angular momentum of the H3 plus molecule. Now there is no pure rotational spectrum that can come off of these things because again there's no dipole moment actually going on, so there's not a pure rotational spectrum, so you can't figure this out in using microwave or radio wave astronomy. So all this stuff has to be done in the infrared. And as I said earlier, there is no discrete electronic spectrum, so we can't see anything. So we're stuck here in the infrared region of this. All right. So as for my quantum numbers of H3+, first of all, we have the angular momentum of our molecule. And first of all, we have I mentioned this earlier. So if I equals 3/2, we call that ortho. That's when all your spins are aligned. And here, if I equals 1/2, we call that para. That's when two are aligned and the other one is against that one there. J is going to be the nuclear motion. So essentially, that's going to be like the rotation of our molecule here. And then K here, that's going to be like the projection of J. So it's, again, this is a little bit beyond what we want to talk about here. But essentially, we have our entire rotation, and then we're basically just projecting this onto the other axis and basically just seeing what that actually is. And then, of course, we have our L2, which is going to be the amount of vibration that we actually have here. Now, what can happen is that there can be L resonances. So, in other words, states that have the same K minus L, these are going to be mixed. So, we're going to start talking about this with the quantum numbers towards the end of this part here. Essentially, instead of having one unique quantum number, because of this mixing, basically there's going to be a lot of uncertainty as to what's actually going on. So it's kind of like if you're standing in a hallway, you don't know if you're in one room or another. So it's kind of like that transition region. There's not a good quantum number that you can assign for that. Then there's this other quantum number right here, which is G, and that's just the rotational part of J that's actually going on there. Now, as for some symmetry, if the G is equal to a multiple of 3, we call that ortho. And we saw that earlier with the earlier spectrum, or the earlier level structure. And if G is not equal to a multiple of 3, then we call that para. And because of the Pauli exclusion principle, levels that are forbidden, if J is even and G equals 0, those levels are going to be forbidden in that kind of a case there. Otherwise, everything else is pretty much allowed. Also, ortho to para transitions, these are forbidden. So it's going to be ortho-ortho or para-para, but you can't have ortho to para. Okay, so when we're looking at our fundamental band, we have to remember here's our ground state energies, but what we're observing is the transition from our ground state to our first vibrationally excited state over here. So the one that we're observing, which has the largest intensities, are the R10 and the R11U. So that's one is corresponding there. Here, the L and the U, that just refers to lower and upper. So as you can see, there's my lower, there's my upper state that's referring to. So these other transitions, they can be observed, but they're just not as intense. And if you're looking for a transition that is going to be weak anyway, you want to get the most bang for your buck. So you want to look for where are your most intense transitions. So the R10, the R11U, these are your most intense transitions here. And again, these are the transitions that you actually see. Here's one of the 3-3 transition that's actually most intense that's being seen there as well. So you can overlap those. Just remember when you're looking at all these spectra over here, and you're lining these up, all these things are being lined up versus the speed at which the gas is traveling. So this will have one absorption wavelength. This one down here is going to have a different absorption wavelength. They've just been put on the same scale where you put basically your 0 as your rest wavelength for both these things, but then they're just Doppler shifted by the appropriate amounts there. Okay, so anyway, that's our 2 transitions, and that's our 3-3 transition that we can actually see in that case. All right, now, of course, there are many, many more vibrational levels that are, in fact, allowed. So right here, that's the fundamental transition. But then you can also have, overtone transitions, hot band transitions, combination bands as well. The little superscripts that we see on some of these over here, this is basically corresponding to what the vibrational angular momentum quantum number is for these different states over there. So these are essentially, different, more vibration or in those particular states. So there's a whole lot of states that have actually been studied for these particular molecules. And yeah, now of course the ones that are most of interest, over here are the ones for astronomy. But a lot of these other ones, they have mainly theoretical interest for that. Although in the case of Jupiter, some of them actually did show up for there. All right, and as for calculation and experiment, what you'll notice is that there's been a lot of calculations on this now. From where I got this source, this is up until about 2001 or so. So things have most likely improved since then. But even at that time, as you can see, the calculated and the experimental values are all within a couple of wave numbers there. So that makes searching for these very sparse transitions up here fairly easy, because you can go and basically just search and say, well, I know it should be around let's say 6,000 plus or minus 3 wave numbers, and you know exactly where you have to actually look there, and then you can fairly easily assign the transitions. Of course, when you're assigning transitions, there's no nice little label actually present. All you really see is a little blip on there, so you have to basically rely a lot on your calculations to determine what your transition actually should be, and then you can just see the drift. Now there's been as you can see, as you get to higher and higher energies, the difference tends to increase depending upon exactly which way they do these calculations. The reason, I believe, is mainly due to how accurately they do their calculations. It's just like if you're doing a Taylor expansion. Eventually, if you go beyond a certain part, those higher order terms that you just left off your Taylor expansion are going to become more and more significant. So that's really the how much time and effort you put into your computation and how much time and effort the computer puts into it really determine how accurate your calculation actually should be. And knowledge like this lets us know exactly, well, where do we need to where do we need these extra terms, or can we ignore them, or wherever else you need to do there. All right, now when you get to extremely high energy levels of H3+, you start actually going into a linear regime. All right, so in a sense, it's almost like the proton has enough vibrational energy that it's kind of like rotating around the hydrogen molecule. So over here, there's my little H3+ ion in this case, and this is going to be the potential energy surface that we're actually looking at. And eventually, when you get to like enough energy, you basically start, getting this thing, kind of like a scalene triangle, whatever. And eventually, you reach this like little barrier, this linearity portion here, where all your hydrogens are, in a line, and then it kind of just, swings back and forms down here. But when you're up in this state, you're essentially, in a different regime and sampling some of the potential energy surface around here, and you have like a whole bunch of very closely spaced, vibrational energy levels that are actually going on. So for this one, this is a lower vibrational state. This is for v equal or nu equals 6. This one over here, this is for like nu equals 7. As you can see, that it changes quite dramatically from there. And again, it just gets very, very messy, and a lot of this is above my pay grade, what's actually going on with this. But what also makes this additionally difficult is it's not just here's your little H2 in the middle, and then there's a little proton going around, but since all these hydrogens are equivalent, it can basically kind of like stop there a little bit, and then this other proton can basically start rotating around. So you have a 3 protons which are basically rotating around one another, interconverting. It's kind of like if you think about the umbrella inversion in ammonia. In that sense, the hydrogens are going on to the other side of the proton. But if you have all 3 protons are identical, now you can essentially have 2 protons go to the other side, or the one in the middle becomes the one on the end, and it just gets very, very messy. I wasn't able never to find like a good animation of this, but essentially just think about all the protons rotating around one another, flipping through each other, and tunneling through each other, because they are so light. They can tunnel as well from a quantum mechanics perspective. So it gets very messy very, very fast. And also this makes this extremely computationally difficult because when you're dealing with it being a planar molecule, it's 2-dimensional. When you are over here in linearity, you've essentially become 1-dimensional. And in those kind of cases, you essentially lose a moment of inertia. Very nasty things happen computationally, because now essentially you have like a 0 here, and you basically have a singularity in the computation, and you have to kind of account for that, and it basically kind of blows up on you. So it's very difficult computationally to actually to model these things. And they have to use things like hyperspherical coordinates and stuff, which again is all way above my pay grade here. All right, here's just another way of looking at the H3+ here. So again, basically this is just representing kind of like the angle between the different protons, and eventually once you get out to this part, here's your pi radians. You've become linear in this sense, and then here's all your like little vibrational levels that you actually have in these cases there. So this is just plotting it out. As you can see, as you get to higher and higher energy levels, these states become closer and closer and closer together, which, as we'll be seeing, makes things a lot more difficult also as well. And this barrier to linearity is right around 10,000 wave numbers. Okay, so that's kind of like a very nice, easy number to actually remember there where that barrier actually is. Now, other molecules do have barriers to linearity. Water has a barrier. Ammonia also has a barrier as well. But we're just talking about the H3+ here today. Okay, so here, like I said, that barrier is right around 10,000 wave numbers, and essentially it's vibrating and inverting, and basically it's, like I said, very, very computationally difficult. Now, down here, again, this would be your ground state. Here's your first vibrational state. These were some of the levels that were studied over here above the barrier to linearity, and a lot of these, as you can see, the main thing that makes these things very, very difficult is a lot of these levels are getting very, very close to one another. And that's why you're going to have actually a lot of mixing actually going on between these different levels. Down here, these are fairly far apart, so you don't have much mixing going on. But up here, very close together, a lot of mixing actually going on. Okay, so here we have a lot of pretty pictures with pretty dots on them. But actually what we're looking at here is the calculated expectation values of our vibrational quantum number for the first vibrational quantum number, for the second vibrational state, the calculated expectation value of your L, your vibrational angular momentum, and then the expectation value of G. So expectation value, you can kind of think about it like the average value. It's basically when you have your quantum numbers here, what do you expect that value to be? So if you have a good quantum number, it should just be on either 0, 1, 2, 3, 4, and so on. Nice integer value. But for your expectation value, that's going to be, well, let's say I have 90% 0, but 10% of the time it appears as 1. So in that case, it would actually be, your expectation value would be 0.1. And if you had, let's say, 50% of the time it's at 0, 50% of the time it's at 1, well, then that means your expectation value would be 0.5. So you're either going to register either a 0 or a 1, but of course, if you do this over many, many trials, your expectation value is essentially the average of all those things. So it's kind of like flipping a coin. You either expect heads or tails, but on the average, you get both for that. Okay. These are color-coded, just to kind of give another dimension of information here. The reds and oranges and yellows, these are for your low J's, and then as you get towards the blues and the purples, these are for your high J's. So what we can see is that low J values, so like for your 0, 1, 2, and so on, these are fairly well, these have fairly good quantum numbers for them. So even above the barrier to linearity here, there's your 10,000 wave numbers, you can see that these are still going to be pretty close. I mean, it might be like 1.8, but you can just round up and say that's pretty close to 2. If you get something like 1.5, that's not a good quantum number. It's basically just in the middle of nowhere. You don't exactly know what's actually going on there. But for assigning what these transitions actually are, what does make it very useful is that some of these do have good quantum numbers when we're dealing with the low J values, which most of the time we actually do have. It makes it easier to actually assign these. And by the way, all this stuff is done computationally. It's not like you can just measure the line and say, oh, well, this is that particular quantum number. All you're doing is basically, computationally speaking, they just figure out what these values actually are here. And then it's really very similar for all these other ones as well. As you go again up for low J's, they have fairly good quantum numbers above the barrier here, but for high J's, it's a complete and utter mess for these things here. All right, so why do we actually have this kind of mess going on? Well, if we look at the previous slide here, notice here for our low levels, these are nice and spaced apart, right? So when we have that nice spacing apart, that means that there's not going to be a lot of mixing between adjacent levels because they are very, very far apart here. So there's not going to be much mixing going on. But when you get to these high levels, these are really close to one another. There's a lot of overlap going on here. And so when that happens, you basically have one level which is really close to another level. And because of quantum mechanics reasons, the wave function has a certain probability of being in one state or the other, and that expectation value is just the odds of it finding one state or the other. When you measure it, it's either going to be one or the other, but on the average, you're going to find it that it's somewhere in between there because of this mixing that's actually going on. Now, why do we have the thing that at high J's things get completely and utter mess? Well, essentially, here's our vibrational states, which have 0 rotation to them. But of course, if we start adding rotation, these are going to add these little fine levels above there. So again, when you're at low states, these rotational states are going to be far away, so you need a heck of a lot of rotation to basically get up to here and start interacting with this one. But when you're up at this stage, a little bit or a lot of rotation basically starts meaning that you start having a lot of overlap with these adjacent vibrational levels, and that's why these states over here, are a complete and utter mess because there's going to be a lot of overlap between, levels which are essentially going to be right on top of one another here. If you're just dealing with low, in those kind of cases, then the values, don't really move that much, and there's not much overlap between adjacent levels, so we're actually on the fairly good side with those. But when you start getting to higher vibrational or higher, I keep saying vibrational, higher rotational levels, that's where all these things basically come into play here. And again, that shows up for all these other plots as well for that. Okay, so I believe that's the end. So anyway, I'll stop that here, and hopefully this thing recorded this time. And then I'll upload that, and then we'll talk next week about the experimental side of doing the H3+. So stay safe, wash your hands, and talk to you next week.